Hello and welcome to Lesson 4. We're going to start this lesson off talking about rational expressions and rational equations. We're going to get into some compound inequalities a little bit later on, but what I want to talk about though is the rationals. This is going to be a review. This should be a review from your previous math class. But I want to make sure that we're all on the same page on what some of these words mean and what our goal of these problems are. So when I talk about rational expressions and rational equations, I'm using this word rational. When you hear this word rational, in a math class at least, you should be focusing on those first 5 letters. Ratio. Ratios are fractions. So rational should mean to you fraction-like, or like a fraction. This is really, really important for us to understand what it is we're talking about so we can kind of understand when I'm talking about a rational expression, what is it I'm talking about? What's our goal of that problem too? So when we're talking about expressions, remember that expressions are things without equal signs. So we're just trying to take a rational expression, something without an equal sign, and simplify it in some way to have an equivalent rational expression. When it comes to a rational equation, though, if we have an equal sign, we're trying to solve it. We're trying to figure out what x values make this equation true. 2 different goals. With the 2 different goals, we also have 2 different things we're allowed to do. So for instance, we're talking about a rational expression, something without an equal sign. We need to make sure that every step from one step to the next is completely equivalent to the step before it. So we're only allowed to do things that are mathematically legal, like multiplying by 1. Multiplying by 1 doesn't change a number, doesn't change an expression. So we can multiply by 1. We can divide by 1. So things like that are perfectly fine if we don't have an equal sign. Now if we do have an equal sign, we can still do those things, but now we have more tools. So if we have an equal sign, we're allowed to multiply both sides of the equation by the same thing. So that gives us a little more to play with, a few more options. And so we do want to pay attention to whether we have an expression or whether we have an equation, because we're legally allowed to do different things depending on what it is that we're starting with. And also, again, remember our goal, that if we have an equation, our final answer should be x equals something. And that something should make the equation true. Whereas when we have an expression, we're going to end with an expression. And it just needs to be equivalent for every value of x to the original problem. So as we progress through this introduction or through this review, one of the things I'm going to try to do is I'm going to try to look at regular everyday fractions and to remind you what the rules in math are with those regular everyday fractions, and then we'll try to apply those exact same rules to a rational expression, to one that basically has x's in it. And the rules are going to stay the same. Rules don't change in algebra. We learn how they work with numbers. They work the same way once you start throwing x's in them. We just got to pay attention to what we were originally doing and apply the same thing once there's x's involved. So, suppose I'm trying to add the fraction 1/2 plus 1/3. Now, one of the things I do want to talk about is just getting a ballpark idea of what your answer is. So, when it comes to this, if we have a half, going back to the old idea of pi, we've got this pie that's cut into 2 pieces, that's a half. A third is to cut it into pieces where a third can fit. So if we're going to add those together, however much shaded we have there, we can see that it's most of the full pie. It's going to be a little bit less than 1, definitely more than half. Now I want to bring this up because one of the common errors that we see when dealing with fractions is just to hope that they're really, really easy and hope that with fractions we just add 1 plus 1 on the top and 2 plus 3 on the bottom and just hope it's as easy as that. Get 2/5. Well, 2/5 is less than 1/2. So if you have 2/5 of something, a fifth would be something like that. Let me see if I can draw this appropriately. Yeah, it's not really to scale. But anyhow, it's something like that. If we have 2 of them, we can see that that's about a half. It's actually a little bit less than a half. So that doesn't make any sense at all. So we know that doesn't work. Going back to the whole idea of pi or pizza or something like that for our fractions, it's hard to add fractions if their denominators aren't the same because there's different sizes. If we look back over the picture that I have drawn there, those 2 pieces of pie are different size. So it's hard to say I have 2 of anything. I have 2 pieces, but they're different sizes. But if this pie here were cut in such a way that my pieces were the same, then I could talk about how many pieces that is. So what we're going to do is we're going to do something that's mathematically legal in order to make that happen. we're going to say, I want to multiply the bottom to make it bigger. So I'm cutting this into more pieces of pi to make it so that it has the same stuff that the other fraction has. So the second fraction has a 3 in the denominator. I would like a 3 in the denominator over here in order to make them the same. Now I can't legally just put a 3 there. That's not okay. What I can legally do, though, is I can legally multiply by 1. 3 over 3 is 1. Multiplying by 1 doesn't change anything. So I just multiply by 1, means I didn't change anything. But now my first denominator has a 3 in it. Now my second denominator would like a 2 in him. That way they become the same. So we're going to play the same game and say, well, if I just multiplied by 2 over 2, now their denominators are the same. And so really the rationale we want to look at was to say, what am I missing that the other guy has? Give them to me in a legal way. This makes it 3/6 plus 2/6. Going back to our idea of pie or pizza, I have both of these cut into 6 pieces. So I have 3 pieces from a pie that was cut into 6, and I add 2 pieces from a pie that was also cut into 6. That gets me 5 pieces of pie from a pie that was still cut into 6 pieces. Your denominator doesn't change when you add, because when you're adding, you're just saying, how many pieces do I have? The denominator only tells you how many the original pie was cut up into. It's the size, basically. So it's the size of the piece, and that doesn't change as you add together. The only thing that changes is how many pieces you have. And so that's how we add with regular old fractions. Let's look at an example of how we can apply that same reasoning to algebra. Now we're looking at an algebra problem that's a rational expression, and we're adding these 2 rational expressions together. And we have to realize what our denominators really are. We want to think about these denominators as a single factor of x plus 2 and a single factor of x plus 3, so that we try to decide what it is that I need to multiply by to make the other one look the same. Even though they both have an x in them, the x isn't the factor. The x isn't what we're multiplying by, so that's not actually something in common between them. That's similar to saying if I had 12 and 13 as denominators, the fact that they each have a 10 in them doesn't really matter. That 10's not in common in terms of a factor. 10 doesn't divide into 12. 10 doesn't divide into 13. So the fact that there's a 10 there doesn't matter. Similarly with our variables, the fact that they both have an x doesn't really matter. What matters is, as I look at the second fraction here, he has an x plus 3 in him. So the first one wants an x plus 3. So we put an x plus 3 in the top and in the bottom. Now as we look from the perspective of the second fraction looks at the first fraction and says, hey, you have an x plus 2. I don't have an x plus 2. I'd like an x plus 2. So we're going to give him an x plus 2, and we do that legally by putting it in both the top and the bottom. And in doing so, now both fractions have the same denominator. We have an x plus 3 over x plus 3, x plus 2, and we have an x plus 2 over x plus 3, x plus 2. So now my denominators are the same, and now I can just add the numerators together. So up top, I'm going to get x plus 3 plus x plus 2. And in my denominator, remember the denominator doesn't change. Once you make them common denominators, once you make the denominators the same, they don't change because that's just how many pieces the pie was cut up into. And now up top, we can combine some like terms. We can get 2x plus 5, and our denominator just stays the same. Now, a little bit later on in this lesson, we're going to talk about simplifying rational expressions. So we should look at this and say, can we simplify this further? And we're going to talk about how to factor the top and see if there's any factors in common. But for now, we can say, nope, this is as good as it gets. There's my answer. Now when it comes to subtraction, not a whole lot changes. I want you to remember something as we progress through this course, that subtraction just means add the opposite. So we could literally just change this to plus -5. And that's really how we want to think about this. This is an addition problem where I got a -5 up there. But I also want to show this example because these denominators look like they're much more complicated. But one of the keys here is to factor them. So let's factor this first one by saying what multiplies to be -10 and adds to be +3. And so that would be x plus 5 and x minus 2. And then similarly, we can factor the x squared minus 4, and that's going to be a difference of squares. That's x plus 2, x minus 2. So once we have these in this nice factored form, now we can look and say, what are we missing? So if we start with the first fraction and look at the second, so we're going to look at the x plus 2, x minus 2. The first fraction already has an x minus 2 in him, so he doesn't need that. What he does need, what he is missing, is the x plus 2. So we're going to put an x plus 2 in the top and the bottom. And again, remember that what's happening here is I'm multiplying by 1. Since I'm multiplying by the same thing in the top and the bottom, anything over itself is 1. So that's all that's going on is I'm multiplying by 1. Now if we look from the perspective of the second fraction and we look at the first one to say, I'm jealous of you, what do you have that I don't have? So he's got an x plus 5 and I don't have an x plus 5. So I want an x plus 5 in the top and the bottom. Now the first guy has an x minus 2, but I have an x minus 2. The first guy has an x plus 2, but I have an x plus 2. So I'm perfectly fine now that both denominators are the same. Now that both denominators are the same, I can just look at the numerators. The numerators are 2 times x plus 2 and -5 times x plus 5. In this denominator, it doesn't matter which order I write those three factors in, but the denominator is going to be those three factors. Remember, it doesn't change when you're adding or subtracting with fractions. Once your denominator is the same, it stays that way. Now we can simplify the top. We're just going to distribute the 2 to get 2x plus 4. We're going to distribute the -5 to get -5x minus 25. And we're just going to rewrite that bottom. I know it's a little tedious to keep rewriting, but we're going to be good little mathematicians and make sure that our steps follow from one step to the next, and that they're equivalent to each other. And now up top, we're going to go ahead and simplify one more step by combining these like terms. What we have here is an acceptable final answer. It would also be okay if we went ahead and factored the top to notice, hey, there's a greatest common factor up there. So it's going to factor this way. And this is not a bad idea to do, because what we're going to cover here in a second is simplifying fractions, and to remember that when we simplify, we're going to factor and then divide out any common factors. So either answer is perfectly fine, but the second one does help us to see that this doesn't simplify any further because there's nothing in common between the top and the bottom. So I've alluded to the idea of simplifying fractions a couple times now, and we're just going to go ahead and officially do it now. The steps to simplifying a fraction are written right here on the screen. Your first step is you're going to factor, and then you're going to divide common factors out. And I want to explain why this is legal so we can understand what is legal and what isn't. Now, if we think about this in terms of numbers, it really is going to make a lot more sense when we get to variables, some algebra stuff. Now, most of us can go ahead and look at 12/16 and say, yeah, this simplifies down to 3/4. There's a 4 in both. They divide out. We kind of do that in our head. But I want to talk about why that's okay. And really why that's okay is just really the opposite of what we were just doing with adding together fractions. We're just going to undo it. So I have it written down here that we're going to factor and then divide common factors. So what's happening here is we're going to take that 12 and say 12 is really 4 times 3. Now we could go down further and call it 2 times 2 times 3 if we really wanted to, but it's not necessary. And similarly for 16, it's 4 times 4, and again, we could go down further to 2 times 2 times 2 times 2. For this problem, it's not necessary, and it's simple enough that we can see that it's not necessary. So this is hopefully obvious that this is okay. Now the next thing is not necessarily obvious, but hopefully easy enough to see that it is okay. And you don't have to write each of these steps out each time, but I want to go ahead and write them out once so we can make sure we understand what it is we're doing, why it's okay, and most importantly then, what's not okay. So we're going to rewrite this as two separate fractions, and that's okay because of how we multiply fractions together. When you're multiplying fractions, you multiply across the top and multiply across the bottom. So undoing them is perfectly fine the same way. So then we want to say, well, what's going on over here? What's 4 over 4? Well, 4 over 4 is just 1. And 1 times anything is itself. So I know that way back at this step here, most of us are in the habit of just crossing off the 4's and calling them good. But if we go back to our directions, I'd specified not to cancel. I think that cancel is a swear word. Cancel is a swear word because we use it in too many situations to the point that we don't really understand mathematically what's going on. We don't understand why was that okay, and why can I not do something that looks so similar? So let me go ahead and do something ridiculous that's similar and just point out what I mean by canceling being bad. Let me rewrite 12 as 10 plus 2, and let me rewrite 16 as 10 plus 6. Then our 10s can cancel, leaving us 2 6ths, which simplifies down to 1/3, right? Well, of course not. Our answer is 3/4. What happened here that wasn't good is those 10s can't cancel. What's really happening is we're dividing common factors. If we look back over at what was legally okay, we had 4 over 4 times 3/4. That multiplication was okay only because it was multiplication. It had to be multiplication for that to work. Addition doesn't work that way, so we couldn't have done it if it was addition. It only worked because it was multiplication. And then the 4 over 4 was 1, and 1 times anything is itself. Now the fact that this is addition over on the right side makes it so that what I did there is just straight up wrong. It's illegal. You can't do that. And that's why I have in bold that we're going to divide common factors. The word factor are things multiplied together. That's what we mean by a factor. Now, of course, you can find a little better definition than that without the word things in them, but the important thing for you to understand is that factors are things being multiplied together. So that's what we can divide out, is common factors, because something over itself is 1, and then 1 times anything is itself. You need both of those. You need the something over itself, and you need multiplication in order to be able to make it go away, to divide it out. In this example, we're being asked to simplify this rational expression. And going back to our idea of simplifying, that means that we're going to factor and then divide common factors. Now the top is a little bit harder to factor because of the fact that we have a lead coefficient of 3. So my suggestion to you is start with the bottom. So if we start with the bottom is much easier. We need to say what multiplies to get you positive 2, but adds to get you negative 3. So that's going to be x minus 2, x minus 1. And the reason I ask it that way then is because now if this thing's going to simplify, I know that my top might have an x minus 1 in it. If not, it probably has an x minus 2. That helps me out with my guess, check, and revise. Because if I know that my first guess has an x minus 1 in it, then I can figure out that the rest has to be 3x plus 2 in order to make sure I'm getting a 3x squared and a negative 2. Now for the check part of that, I need to check my o and my I. My o is negative 3x, my I is positive 2x, That gets me negative x, which is in fact what I wanted. So that is the correct factorization, but if it wasn't the correct factorization, I would have taken the guess with the x minus 2 and saw what was there. So by knowing what factors are there, we kind of have some good guesses, similar to if I was looking at some crazy numbers, like let's go ahead and say I had 124 up here, and I had, let's go ahead and say, I don't know, 12 in the bottom, and I was trying to simplify that. Well, I'm not going to start with trying to factor 124. I'm instead going to say, well, 12's pretty easy. He's got a 4 and a 3 in him. I know that 3 doesn't go into 124, so let me see if 4 does. So instead of factoring 124 into all its parts, I'd be smarter about it and just say, hey, if I do the easier one, then I'll see if there's anything in common. That's a little easier. So back to our problem at hand. We have an x minus 1 in the top and the bottom. They divide out. That leaves me with a 3x plus 2 in the top and an x minus 2 in the bottom, and that's it. Now remember, those 2's look like something should have happened, but there's addition and subtraction that's separating those things. That means that 2 isn't a factor. We can't divide out a common factor. That 2 is a term. So this is as good as we can get. Now we're going to step up to talk about multiplication. Now we're multiplying these fractions together. We could go ahead and multiply across the top, multiply across the bottom. But I gave these big numbers on purpose to kind of prove a point as far as algebraic expressions are concerned. So if I did just multiply across the top and say 121 times 63, I could get 7,623 on the top. Then on the bottom, I could do the same thing and say, what's 35 times 88? And the answer is 3,080. And that's all well and good until I got to say, well, is that in simplest form? Can I simplify that fraction any further? I say, I don't know. So how do we simplify that fraction? Well, we factor it. We say, what things multiplied together equal this? Well, I can tell you, 7,623 is, 121 times 63. And 3,080 is 35 times 88. The point being, why did I multiply them together in the first place? No good reason. So we're going to erase all of that and say, if my overall goal is going to be to simplify this by dividing out common factors, why don't I just start with factoring? And that's what I would do. If I was multiplying this, I don't need a calculator for this. 121 is 11 times 11. 35 is 7 times 5. 63 is 7 times 9. And 88 is 8 times 11. Now we could go a little bit better with the 9 and the 8 if we really need to. But let's look at what happens now. I've got an 11, oops, I want to switch to a highlighter. I have an 11 in the top and the bottom, so they're going to divide out. I also have a 7 in the top and the bottom, so they're going to divide out. And then that's it. There's another 11 in the top. There's no 11 in the bottom. There's a 9 in the top, which could also be a 3 and a 3. There's no 3s or 9s in the bottom. So nothing else simplifies. Now we can go ahead and multiply. 11 times 9 is 99. 5 times 8 is 40. That's our answer. So we didn't need to worry about the whole 7,623 divided by 3,080. That wasn't necessary. We could simplify it earlier on and end up with a nice happy number that we can multiply in our head. And we want to do the exact same thing when it comes to rational expressions that we're multiplying together. Is we want to factor everything down, divide out any common factors that we can, and then worry about what's left. So for this multiplication problem, it's all going to boil down to factor, factor, factor. That's the name of the game. We're going to factor all 4 of those polynomials. We're going to divide out common factors that are in both the top and bottom, and we're going to see what's left. So we're going to start in the upper left, and we're going to say what multiplies together to equal -4, but adds to be -3. And so that's going to be a -4 and a +1. There's our upper left. Then in the lower left, I've got x squared minus 16. That's a difference of squares, so that's x plus 4, x minus 4. Now if I go to the upper right, I need something that multiplies to be positive 4, but adds to be positive 5. So that's going to be 4 and 1. And then in the lower right, I need something that multiplies to be negative 3, but adds to be negative 2. So that's going to be negative 3 and positive 1. Now once I have all these factors written out, now it's just a matching game. I've got an x plus 1 in the top and bottom. They divide out. I've got an x minus 4 in the top and the bottom. They divide out. And I have an x plus 4 in the top and bottom. They divide out. All I have left is an x plus 1 in the top and an x minus 3 in the bottom. And remember, those x's don't divide out because those aren't factors. Those are terms. And so that's as good as we can get. There's the multiplication problem. With this example, we're looking at division of rational expressions. And just like with fractions, a division problem can always be rewritten as multiplication by the reciprocal. And that's exactly what we want to do in this case, is the first fraction doesn't change at all, but then the second one becomes multiplication by the reciprocal. And remember that reciprocal basically just means flip the fraction. So that's how we're going to start this one off, and then once we do that, it's just a factoring game again. So as far as our upper left, that doesn't factor, so it's just a factor of x plus 2. Similarly, the lower left is just x minus 2. The lower right, the x squared minus 4, that's a difference of squares, so that's just going to be our x plus 2, x minus 2. And then in the upper right, we're looking for things that multiply to give us negative 2, but add to give us positive 1. So that's going to be negative 2, positive 2, and negative 1. And that should add together to equal positive 1, multiply to be negative 2. And once we have that, now we can do the whole matching thing. We've got an x plus 2 in the top and the bottom, so those divide out. We don't have an x minus 2 in the top and the bottom. And so that's as good as we can get. So up top, we've got an x plus 2 and an x minus 1. And in the bottom, we've got a couple x minus 2's. So we can either write it as x minus 2 times x minus 2, or we can write it as x minus 2 squared. Now, if you really wanted to, you could go ahead and FOIL out the top and end up with a trinomial. In the bottom, you could also multiply that out. It's not really necessary, though, so you may as well leave it in the factored form, because not only does it show you that it doesn't simplify any further, you're not going to make any mistakes as you try to multiply it out and end up getting a wrong answer because you made a mistake in extra steps. So you don't want to do that. So our next topic is going to be about solving rational equations. So everything we've done before this has been rational expressions. We've done the addition, subtraction, multiplication, division, and simplifying with the rational expressions. And as I mentioned in the intro to this lesson, with equations, we open up the door to a little more that we're allowed to do, because once we say there's an equal sign, we're allowed to do the same thing to both sides of the equation. So up here on the screen, I have some review that we'd covered previously in the semester. It was actually from lesson 1 to say anytime we have fractions involved, we can just say, hey, fractions suck. Let's get rid of the fractions. And the way we do that is we multiply both sides of the equation by the LCD. That's going to clear the fractions. Once we've done that, then we just solve whatever's left. Sometimes we're left with a linear, sometimes we're left with a quadratic. Whatever we're left with, just solve it and get an answer. And so that's what we're going to do here as a refresher, and then we'll see how that compares when we start throwing x's into the bottom. So let me give myself some room to work here. The LCD between 3, 2, and 4 is going to be 12. Now sometimes I use this shorthand notation that I'll put parentheses around the entire equation. This isn't the best math in the world, but it kind of lets me know I'm going to multiply both sides of the equation by 12. What this really means to me then, when it comes to fractions, is I'm putting a 12 into the top of every fraction. So this becomes 12 over 3x minus 12 over 2 equals 12 over 4. Now remember, we're not putting this in the bottom. Our goal here is to get rid of the bottom, so we want stuff in the top. This is cool since we have an equation, we have an equal sign, that we're allowed to do this. We're allowed to multiply both sides of the equation by the same thing as long as that thing isn't 0. Now we're going to simplify what we got. We got 12 thirds is 4, 12 halves is 6, 12 fourths is 3. Now we have a ridiculously simple problem. So now we're just going to go ahead and add that 6 to the other side. We're going to divide by that 4. We've got ourselves a nice happy answer of x equals 9/4. No real crazy work that needed to be done. Once we cleared those fractions, it's a piece of cake. And that's what we hope to have happen when it comes to rational equations as well. Now, when it does come to solving rational equations, I do have a third step in here that ends up being really important. And this is important because of something that I said very briefly and quickly as I was solving that last equation. I said that we're allowed to multiply both sides of the equation by anything we want as long as it wasn't 0. You're not allowed to multiply both sides of the equation by 0. So we need to make sure that whatever answer that we get when solving a rational equation doesn't make the denominator 0. For two reasons. One, it would have meant that in solving the equation we multiplied by 0 on both sides, which isn't legal. It also means that we would be dividing by 0 in our equation because we have a 0 in the bottom. Either way, that's not good. So this is going to be one time in this course that no matter what answer we get, we better check it to make sure it's actually going to work for a very specific reason. There's going to be 3 times throughout this course that happens. You have to check your answer. And it's really important to understand when that is and why that is. So the reason being that we got to make sure that we never have a denominator as 0 here. So if our answer makes the denominator 0, we're going to throw it out. If we had one potential answer and that answer made the denominator 0 and we throw it out, then we're going to say there's no solution. And that's going to be the answer to our equation is no solution. Now, if, on the other hand, you had 2 potential answers and you throw one of them out, then you just report the answer that works. You don't report x equals 5 and no solution. That doesn't make any sense. If you have 2 answers that could work, one of them doesn't because it makes the bottom 0, you just report the one that does, and that's it. So here's an example of a rational equation. We do want to multiply both sides of the equation by the LCD. What sometimes is helpful is to factor all the denominators. Now in this case, the x squared minus 1, hopefully you can kind of picture in your head as x plus 1, x minus 1, which happens to be the factors that are there already. So hopefully we can do this one without actually literally writing out the factored version, but sometimes it does help. Now something else that I'll sometimes do personally is off to the side, I'll remind myself, no matter what I get, x can't be negative 1 and x can't be 1. Those are the values that would make my denominator equal to 0, so I'm going to write them off right off the get-go, and that way I don't accidentally report them, because sometimes you go through a whole bunch of steps, and then you sort of get your answer, and you're so happy because you went through all these steps, and you forget about that step to say, oh yeah, let me make sure my bottom wasn't 0. So we're going to multiply both sides of the equation by the LCD. Oops, what did I write 3 for? I have no idea. So our LCD in this case should be x plus 1 times x minus 1. So we're going to multiply that on both sides of the equation. But again, in other words, what's going to happen here is we're going to multiply this into the top of each of them. Because literally I'm multiplying it on the left, so I distribute, I multiply on the right, it ends up in the top. So I'm going to have, oops, I'm going to switch back to black ink. I'm going to have 2 times x plus 1, x minus 1 over x plus 1. Then I'm going to have 3 times x plus 1, x minus 1 over x minus 1. And then equals 5 times x plus 1, x minus 1 over x plus 1, x minus 1. Now, I know this is a lot to write, and I know a lot of people like to skip steps, but I will tell you, when you write out every step, not only are you less likely to make mistakes, because so much is going on in your head. But also it's easier to find your mistakes and see where they happen if you write out all your steps. But when you start to skip steps, you're starting to do more inside your head, and that's when mistakes happen. We're going to write it out. And so now we're going to say, I have an x plus 1 over an x plus 1. Those guys divide out. I've got an x minus 1 over an x minus 1. Those guys divide out. I've got an x plus 1 over an x plus 1. They divide out. I've got an x minus 1 over an x minus 1. They divide out. So all I'm left with from the first fraction is a 2 and an x minus 1. From the second fraction, the 3 and the x plus 1. And on the right-hand side, just left with 5. And at this point, we have a pretty straightforward linear equation to solve. We're going to go ahead and distribute. We're going to combine some like terms. We're going to subtract the 1 to the other side. We're going to divide by the 5. Get 4/5. 4/5 was not one of my disallowed values. So remember, I wasn't allowed to have 1. I wasn't allowed to have -1. And so my answer actually is 4/5, and it works. Now, I don't have an example set up or practice problem set up for this particular idea, but I did want to give you a quick reminder about something from earlier in this course that you actually learned in the previous course as well, and that's what a negative exponent represents. Because we can have negative exponents where this doesn't really look like a rational equation type situation, but it actually is. So if we have negative exponents, remember that a negative exponent means take the reciprocal of this base. But you also want to be careful about what it is that we're taking the reciprocal of. So x to the negative first means to take the reciprocal of x squared. So it becomes 1 over x squared. Now where this becomes tricky then is in this middle term. It's tempting to say, well, this means 1 over 9x because we had 9x to the negative first power. But that's wrong. Is 9 really being raised to the negative first power? No, order of operations tells us PEMDAS. Please excuse my dear Aunt Sally. Parentheses first, then exponents, then multiplication and division from left to right. And this is 9 times x to the negative first. And so the exponent's being applied to the x, and then I'm multiplying by 9. So the 9 actually stays in the top, and only the x goes in the bottom. So now this would become an actual rational equation where I could multiply both sides of the equation by x squared. That would give me x squared over x squared plus 9x squared over x plus 8x squared equals 0. That would give me 1 plus 9x plus 8x squared equals 0. And I'm not going to complete the problem from here, but you could factor it, set each factor equal to 0, and go from there, keeping in mind that your denominator can't be 0, so x can't equal 0. But just remember that a negative exponent means to take the reciprocal and pay attention to what it is that we're raising to the negative exponent. Make sure that coefficients stays coefficients. We're going to shift gears now. We're shifting gears away from the rational expressions and rational equations in order to talk about sets. Sets of values. Now, in the past, from as early as grade school, you talked about finite sets, where finite sets where you're given a list of numbers and they're in there. And at some point, you even started learning about Venn diagrams. And Venn diagrams were a cool way to see where your sets overlapped at. What elements were in both of your sets? That's something that you call the intersection, and we're going to continue to use that terminology. You also sometimes looked at a Venn diagram and said, what is a list of all the elements that are in either set? And you called that the union of the sets, and we're going to use that notation as well. Now what we want to do, though, is we want to be able to step beyond that and say, all right, that's all well and good if we've got these finite sets with a list of elements in them. But what if I have an infinite set? What if I have all the numbers bigger than 5 And not even just whole numbers. All the numbers bigger than 5. That's an infinite set. How do I start doing set operations with those? How do I take intersections and unions with those? And the simple answer is we're going to do it graphically to picture what's going on. And then we're going to have a way to represent what that picture is telling us in symbols. And so we're going to talk about symbols, and we're going to talk about how we can use symbols to represent an idea. And it's really important that we have these symbols to make sure we're on the same page. And that what I have in my head is exactly what you understand by using good symbols. So that's the first thing that we're going to do is talk about some of the symbols. So what if I have the set of numbers 1, 2, 3, 4? So this is a finite set. There's only 4 elements in this set. The notation that we use then are the curly braces. And we just list out 1, 2, 3, 4. And we end the curly brace. So that's what the curly braces are for. The curly braces are for finite sets when we're just going to list out, here's the elements in the set. Now we do sometimes use the curly braces to represent an infinite set, but it becomes kind of weird and confusing. So we have better ways of doing that. What we typically do is we typically use what's called interval notation. And interval notation is a way of saying all the numbers from here to here. But then we got to be careful and say, all right, at those endpoints, do I want to include that endpoint or just all the points that get really close to it? And so we have different notations for that as well. So the symbols that we use to indicate, let's include this value. Well, one symbol that we use is if we're talking on the number line, we use a dot. We use a closed-in circle on the number line to say, let's include this value. And you can think about this in terms of way back to like kindergarten. If I was looking at the number line and said, hey, where's 5 at? You put a dot at 5. That's it. That means include this value in the numbers I'm talking about. Now, when it comes to interval notation, we have a couple other symbols that we use that mean include this value. And they're going to be a bracket in either direction. The left bracket is the left endpoint is included. The right bracket means the right endpoint's included. But these are the 3 symbols that we're going to use for now for talking about include this value. Once we get into 2 dimensions, an x and a y variable, we'll need to talk about other things. But for now, this works. Now, symbols that mean don't include this value, on the number line, we're going to use an open circle. Almost like a little force field around that number that says you can come really close to this number, but I'm going to leave this number as hollow, meaning it's not included. Now, as far as interval notation is concerned, we use parentheses to indicate this value is not included. So we're going to use the open circle on the number line, parentheses with interval notation to mean this value is not included. So if I wanted to list the set of all numbers between 1 and 4, including 1 and 4, we'd write that with the bracket with the 1 and a bracket with the 4 and a comma in between. Now, order does matter. We list the numbers as they'd be on the number line from left to right. So the smaller number first, followed by the larger number. And what this notation means is more than just 1, 2, 3, 4. These 2 things are not the same because the interval notation that we just wrote also includes 1.1 and 2.5 and 3.99999999999. And even then irrational numbers. Pi is in that interval. So interval notation is all the numbers, not just the whole numbers. Now, if I want to list the set of all numbers between 1 and 4, we're not including 1 nor 4, then we'd use parentheses. Again, order matters. And it's important to realize what this means, that this means 1.0000000000001 is included in this set. 1 isn't, but 1.0000001 is. 4 is not included, but 3.999999999 is. So everything in between 1 and 4 is part of this solution, part of this interval, but 1 and 4 themselves are not. So let's talk about the set of all numbers smaller than or equal to 1. So there's a couple ways we could write this. The way that I want you to write it is to say, all right, well, let me think about the number line for a second. Let me come down to the number line and say, on the number line, I'm saying include 1 and include everything to the left of 1, everything smaller than it. So if I want to think about this in terms of interval notation, I need a left endpoint and a right endpoint in order to write an interval notation. Now for my left endpoint, I continue on forever, so that number is what we think about as negative infinity. It's as far to the left as we can go. The right endpoint is 1. Now as far as our notation, we're including 1. Negative infinity isn't really a number. So your infinity and your negative infinity are always used with parentheses because they're not really numbers. You can't actually stop at infinity or negative infinity and say, I'm there, I reached it, I'm going to include this number. It's not a number. So we always have to use parentheses for those values. Now, we have one more example we want to look at. The set of all numbers between 1 and 4, as well as the numbers between 5 and 6. So let's look at a number line again and kind of picture what's going on. We got all the numbers between 1 and 4, as well as between 5 and 6. Now I didn't specify whether the endpoints are included or not, so because I said between, let's go ahead and say they're not included. Just the ones between. So we have two separate intervals that have a gap between them. We have a way of representing that. So the first interval has a left endpoint of 1 and a right endpoint of 4, parentheses for both. The second interval has a left endpoint of 5 and a right endpoint of 6, also parentheses for both. And the symbol we're going to use between those two intervals to represent the fact that I want both of them in my final answer is the union symbol. The union symbol looks like a capital U, only it doesn't have the little stick at the end. It doesn't have the little vertical line. But that symbolism there represents the numbers between 1 and 4, as well as the numbers between 5 and 6. The union symbol just says, hey, both of these answers, or both of these intervals, are part of my answer. So suppose I have two finite sets. Set A has the elements of 1, 3, 5, 7, and 9, odd digits. And set B has 2, 3, 5, 7, prime digits. Now, the symbol that's written at the bottom of your screen right now, that symbol that kind of looks like an upside down version of the union symbol, that's the symbol that we use for intersection. So the intersection of two sets is the elements that are in both at the same time. So as I'm looking at these, 1 is in A but it's not in B. 2 is in B but not in A. 3 is in both. 5 is in both. 7 is in both. And 9 is in one but not the other. So my actual answer to this is going to be the set of 3, 5, and 7 listed out, and so we use the curly braces. Now there is another way we could have organized our information here, and it might not be necessary in a problem like this, but I want to point out this organization because it works nicely for what we're going to be talking about after this. We could have looked at each of our sets on the number line. So we could have looked at 1, 2, 3, 4, 5, 6, 7, 8, and 9. And we could try to represent set A and set B here. So I'm going to go ahead and use blue to represent set A. Set A was 1, 3, 5, 7, and 9. And I'm doing this above the number line on purpose, and I'll explain why in a second. Set B, also above the number line, was 2, 3, 5, and 7. And so if I want to figure out where the intersection is, this visual representation hopefully makes it easy because I can just look at each number and say, do I have blue and red above it? So when I'm looking at 1, I can see that blue is above it, but red isn't. If I look at 2, red is above it, but blue isn't. But when I look at 3, they're both there. When I look at 5, they're both there. When I look at 7, they're both there. And when I look at 9, blue is above it, but red isn't. And so this tells me 3, 5, and 7 are the numbers that have both A and B stuff. So 3, 5, 7 is the intersection. So now we're going to get into the infinite sets that I was alluding to earlier. So we're going to have two different infinite sets that we want to take the intersection of. But instead of using that intersect symbol like we do with a finite set, we actually use the word and. The word and means the same thing as intersection when it comes to these infinite sets. And then the way that we're going to solve these problems that have ands in them, these intersection problems, is actually the same as the way that we did the graphical interpretation of that intersection of finite sets. We're going to use a number line. We're going to visualize one set above the number line, visualize the other set above the number line, and just say, hey, where do I have both blue and red at? And if I can identify that, then there's my answer. Once I have my answer graphically, I can interpret that answer and write it in interval notation. So to list out steps, if you're kind of a work-by-steps kind of person, we're going to assign a color to each inequality, and the inequalities are representing these infinite sets. We're then going to graph each of the individual inequalities using the color we designated back from step 1. Then we're simply going to reread the original problem with the word and in there, and we're going to shade whatever actually answers the question. Once we have that final shading, we're going to write the answer in interval notation for whatever that final answer happens to be. So let's go ahead and look at an example. So here's an example of two infinite sets. X is greater than 3 is an infinite set. X is less than or equal to 10 is an infinite set. There's an infinite number of numbers that are bigger than 3. There's an infinite number of numbers that are less than or equal to 10. So our first step was to identify colors to each of these sets. So I'm going to call the first set my blue set and the second set my red set. I'm going to label my important numbers on the number line in the right order as you go from left to right. So the smaller number comes first, the bigger number comes second. So I'm just labeling these numbers on here, and maybe this will be part of my answer, maybe it won't, but these are just the important values. Now above the number line, and this is important that we do it above the number line, because we're kind of laying out our scratch work is kind of what we're doing. The actual number line itself should be our final answer. So to lay out our scratch work, we're going to take x is greater than 3. X is greater than 3 would be an open circle at 3, and everything larger than that. And notice that I'm extending that line all the way to the end. I'm not just doing a small line with an arrow. And this is important to be able to visualize this problem properly. Then I also have x is less than or equal to 10, and I'm using red for this. So since I'm allowing equality to 10, I'm going to use the closed circle to say I'm including that. And less than means everything to the left of it. So this is my scratch work. Now I need to use this to figure out what it is that I need to be shading for a final answer. What I want you to visualize here is that we broke the number line up into 3 chunks. We have the chunk that's to the left of 3. We'll call that the leftmost chunk. We have the chunk that's in between 3 and 10. We'll call that the middle chunk. And we have the chunk that's to the right of 10. We'll call it the rightmost chunk. We need to look at each of these chunks, and we need to say, do they satisfy the problem? Our problem at hand, and here's how to make it as simple as possible. Ignore the x's, ignore the numbers, and just look at colors. Blue and red. That's what our original problem says. Blue and red. My final answer is anywhere that I have blue and red. So if I look at my leftmost chunk, I can say in this leftmost chunk over here, do I have blue and red? And the answer is no. I only have red. So then I look in the middle chunk and say, do I have blue and red? Why, yes I do. Because I do have blue and red, I'm going to shade this interval. Then I'm going to look at my rightmost chunk and say, hey, do I have blue and red? Nope, I only have blue. So that's not part of my final answer. Now I do have a little more work to do. I have to look at the endpoints themselves. So at the endpoints of 3 and 10, I need to figure out what's going on. So at 3 itself, do I have blue and red above? No, because blue has an open circle. So for that reason, I need an open circle here at 3. Over there at 10, though, I do have both blue and red directly above it, so I'm going to use a closed circle there. This is the graphical interpretation of my answer. But I also want interval notation, so I need to go from this graph to write it in interval notation. And I do that by saying it's everything from 3 to 10. We always go left to right, order matters. And then we use the right symbols. So at 3, I'm not including that point, so I use a parenthesis. At 10, I am including that point, so I use a bracket. And that's the answer to this example, is from 3 to 10, not including 3, but including 10. So hopefully these compound inequalities are so far pretty easy. We plot the line, we plot the other line, we look at where there's overlap, if it's the word and, pretty easy, then write that interval notation. Now, not every single compound inequality is going to be as simple as just saying x is greater than 3 and x is less than or equal to 10. We're going to have some math to solve. So we're going to have things like 2x minus 1 is greater than 5, 1 minus x is less than negative 5, and we're going to try to make them look as easy as that first example. So we're going to try to get the x by itself. And so I just want to remind you that when you're solving an inequality, do it just like an equation. You can multiply the same thing to both sides, add the same thing to both sides, divide, subtract, do the same thing to both sides to get the x by itself. The only added rule is that if you multiply or divide by a negative, then you got to change the inequality sign. If it was less than, make it greater than. If it was greater than, make it less than. The rationale behind this is hopefully very easy and simple. Now, we can get into mathematically, and I'll talk about that in a second, but the basic idea is pretty simple. The basic idea is that when you multiply by a negative, you're taking a reflection. We talked about that with graphing previously. Think about a mirror. If you wave at the mirror with one hand, let's say your right hand, what waves back at you? Your left hand. If you wave with your left hand, the right hand's waving back at you. That's what's happening, is it's flip-flopping. Things that were on the left are now on the right. That's why we got to change the inequality sign. Because once you multiply or divide by a negative number, things that were on the left are now on the right. So on the number line, think about the numbers 2 and 3. Which one's bigger? 3, duh. What if I multiplied each of those by negative 1? Negative 2 and negative 3. Which one's bigger? Well, now the negative 2 is bigger. Once you apply the negative, it flip-flopped the order. That's why we got to change the inequality sign anytime we multiply or divide by a negative number. Let's go ahead and solve these two inequalities. We can go ahead and add 1 to the other side, and then divide by 2. We're dividing by a positive, so no big deal. The inequality sign stays the same. Happy, happy. Now for the second inequality, we're going to subtract 1, then multiply by negative 1. Because we're multiplying by a negative, here's where the inequality sign has to change. The other important thing that copies down from step to step is this important word and. So remember, this word and is kind of like the operator in between these two sets. It's like an addition or subtraction sign. So without the word and, we can't really do the problem at all. That'd be like saying, hey, can you do this arithmetic problem for me? 2, 3. Well, it kind of matters for your answer whether it's 2 plus 3, 2 minus 3, 2 times 3, or 2 divided by 3. It really matters. And the same thing goes for this word and, because we're going to look at the word or in a minute. The word and is really important to keep there because that's going to change your answer. If this were an and versus an or, your answer will be different. So let's go ahead and finish solving this problem now. So we're going to go ahead and call the x's greater than 3 our blue. We're going to call the x's greater than 6 our red. And we're going to go ahead and draw a number line. So we got ourselves a number line. We're going to label the two important points, 3 and 6, in the correct order. And then above the number line, we're going to do x is greater than 3. So that's an open circle at 3, and we'd be shading everything to the right. Again, this is done above the number line because it's our scrap work. X is greater than 6. Above the number line, it's our scrap work. So now again, we have broke the number line up into 3 chunks. Left, middle, right. Over here on the left, my problem is asking for blue and red. Do I have blue and red? No, I do not. I don't shade it. How about in the middle? Do I have blue and red in the middle? No, I do not. I only have blue. How about on the right? Do I have blue and red on the right? Absolutely. So because I do, I'm going to shade over here on the right. Now, red had an open circle, so I don't have both blue and red at 6 itself. So my final answer is from 6 to infinity. I'm not including 6, so I use a parenthesis. I never include infinity, so I also use a parenthesis. And that's my final interval notation answer for this compound inequality. So now let's go ahead and look at the union of two finite sets. So in my overview, I was talking about this in regards to Venn diagrams where you kind of said it's all the elements that are in either set A or B. And that's exactly what it means. So the union is to include everything that comes from either one, from set A or from set B. So if I want to find the union of these same two sets, we're basically going to list out any number that we see at all. We're just going to list each number once. So the number 1, I see it, so I'm going to list it. The number 2 is there, so I'm going to list it. The number 3 is there twice. I still only list it once. I don't care that there's overlap. And so then there's also a 5 and a 7 and a 9. Now, just like with the intersection, we could look at this graphically to try to make sure that we can get everything and make sure we didn't miss something by sort of just going through and looking at it. So we could do that again by looking at the number line and saying I got these numbers 1 through 9. Remember that A, if we want to do A as blue, were the odd numbers. So that was 1, 3, 5, 7, and 9. B, which we're going to use red for, was 2, 3, 5, 7. It was our prime digits. So 2, 3, 5, 7. And for the union, basically what we want to look for is to say, do I have blue or red? Either one. If either one's above me, it's part of the answer. So there is something above 1. There is something above 2. There is something above 3. There's not something above 4. There is something above 5. There's not something above 6. There is something above 7, not 8. And there is something above 9. So graphically, our answer is 1, 2, 3, 5, 7, 9, and that is what we got up there as well. Okay, so now we want to look at the union For an infinite set, the word that we use for that compound inequality is the word or. Now we're going to solve this compound inequality in the same way as we solved compound inequalities with and. We're going to start off by identifying a color to each of the infinite sets, each of the inequalities. So I'm going to call one of them blue and the other one red. I'm going to label my two important points. So in this case, it was -2 and 5, and again, in the right order. And then above the number line, I'm going to go ahead and graph each of these inequalities. So we had x is greater than 5, so that's not including 5, and it's everything to the right of it because it's greater than. And again, we're doing this above the number line. This isn't the answer, this is the work. Then we have x is greater than or equal to -2. So we're going to do a closed circle for the -2. And it was greater than, and so everything to the right of it. And again, the closed circle is the or equal to, saying that equal to was okay. So this is our work so far. Remember, this is not the answer yet. We're breaking our number line up into our 3 chunks, left, middle, right. And now if we go back to the original problem, again, ignoring the x's, ignoring the numbers, our original problem is simply blue or red. I want to include anything in my final answer that has blue or red above it. So if I look at my left chunk and say, do I have blue or red above me? I do not. That left chunk, that left chunk does not have blue or red. So we're not going to include him in the final answer. But if I look at the middle, do I have blue or red here? Well, yes, I do have red. So that means I want to include the middle in my answer. If I look to the right chunk, do I have blue or red here? Yeah, I have both. I don't care that it's both, just like in the finite sets, I didn't care that they both had 3, 5, and 7. Same thing here. I don't care that I have both blue and red. I do have blue or red. So this means the middle and the right are both shaded. And at the endpoint of -2, I am including that because I do have red or blue above it. Now that I have a graphical answer here, I have a graphical answer on the number line for where I have blue or red. The left endpoint of this is -2. The right endpoint is positive infinity. Notice I'm not listing 5, just as I'm not listing 6, 7, 8, 9, 10, 11. 5 is included in the interval, but it's not an endpoint to the interval. It's a middle part of the interval. The endpoints to this interval are -2 and infinity. Now, as far as the symbols we want to use, we need a bracket on the -2 to say that this point's included. And we need a parenthesis on the infinity because infinity is never included. And this is our final answer in interval notation. So here's an OR compound inequality that we got to solve first. And so again, we're just going to solve this like it's an equation, except if we have to multiply or divide by a negative number, we're going to change the inequality sign. So on this first one, we're going to add the 3 to the other side. Then we're going to divide by 4. For the second one here, we're going to subtract the 3. And then when I divide by -2, I change the inequality sign. And we maintain that word, which was or, in between them. We're going to define one of them to be blue and one of them to be red. And then we're going to graph some sort of number line and label the important points. And here's where it's kind of cool, because we got this fraction. I don't care what fraction this is even in between. All I care about is that 5/4 is something less than 4. And those are my two important values then. So above the number line with the blue, I have including 5/4 and everything to the left of it, because it was less than or equal to 5/4. Now with my red ink, I was including 4 and everything to the right. So now back to my final answer. Remember, this is just my work. This is not a final answer. It depends on whether I have an or an and on how I get my final answer. I broke the number line up into 3 chunks, left, middle, and right. And I need to look at each chunk to decide, do I have blue or red? If the answer is yes, I shade it. If the answer is no, I don't. So the leftmost interval, do I have blue or red? Yes, I have blue. So I'm going to shade that. For the middle interval, do I have blue or red? No, I have neither one in the middle, so I'm not going to shade the middle. On the right, do I have blue or red? Yes, I have red, but more importantly, yes. That's all I care about, if it's yes or no. So now I have both the left and the right shaded. So I have one interval that goes from negative infinity to 5/4. I have a second interval that goes from 4 to infinity. And when I have two separate intervals that are disjoint, that have a gap between them, I just put a union sign between them. So I really want to point out that that union sign in a final answer is only placed there if we have two disjoint intervals. We don't want to try to come up with a rule of it comes whenever we have an or in this situation. Don't come up with rules like that. If your final answer has two disjoint intervals, you need the union sign between them. We will never, ever, 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 ever have an intersect symbol in a final answer. So please be aware of that, because an intersection is a problem that we can find an answer to. We're always going from the graph, from the number line, to interval notation. I'm going to go ahead and wrap up this lesson with a couple examples that are just some weird situations, but I just want to remind you that we don't assume anything based on the work. We just do these steps over and over again, where we do the work above the number line, then we go back to the original problem and say blue and red, or blue or red, and figure out where it's shaded on the number line, then get the interval notation. Just keep following those steps over and over. So we're going to say this first one is blue. We're going to call the second one red, and we're going to do a number line. We're going to have a 3. We're going to have a 5. So we broke the number line up into 3 chunks. We're going to do each of these graphs above the number line. So the first one was greater than 5, so we're not including 5. We shade everything to the right. For the red one, we don't include 3. We shade everything to the left. Now what's really, really important is this word and. If we look at the leftmost chunk, do I have blue and red? No, I don't. So I'm not going to shade that. In the middle chunk, do I have blue and red? No, I don't. So I'm not going to shade it. In the rightmost chunk, do I have blue and red? No, so I'm not going to shade it. So what did I shade? Nothing. I have a blank number line. That means my final answer is no solution. This is also why we do the blue and the red above the number line. We don't want to put stuff on the number line and all of a sudden say, ooh, I got stuff shaded. The answer is supposed to be no solution. Now, if we look back to the original problem, common sense tells us there's no solution. The original problem is saying, I'm looking for a number that's both bigger than 5 and smaller than 3 at the same time. There's no such number. And if we look visually at what's going on the number line, we're looking for where those two things overlap at, and they don't overlap. So I do want to point out that this looks really similar as far as the work, as far as above the number line, to our example 11. Example 11 had the blue going in one direction, the red going in another direction, and we didn't have no solution. But that's because we had an or. The word that we have makes all the difference in the world. Just like 1 plus 1 is not the same thing as 1 minus 1. You get two different answers. You get two different answers if you have an and versus an or. So it's really important just to go through your steps and not try to say, when my lines are pointed opposite directions, the answer has a union or anything crazy like that. Just do the problem. Do the work, figure out what gets shaded, and then get the interval notation. So let's go ahead and look at one more. Now we'll again go through our first steps of saying this guy is blue, this guy is red. We got ourselves a number line. The important points are 3 and 5. With the blue one, we do not include the 5. We shade stuff to the left. With the red one, we do not include 3. We shade stuff to the right. But it's again important that we have the word or here. You'll get a different answer if it's an or versus an and. Because this is or, we start off with the left chunk and say, do I have blue or red there? And the answer is yes. So we shade. Then we look at the middle. Do I have blue or red there? Yes, and so we shade. Then we look at the rightmost chunk. Do I have blue or red there? Yes. So if you look at what I've shaded the whole number line. The leftmost endpoint that I shaded is negative infinity. The rightmost endpoint that I shaded is positive infinity. I shaded everything from negative infinity to positive infinity. That's everything. So as you can see, we can get intervals that have two endpoints, from 2 to 5. We can have an interval that has negative infinity on one side and number on the other. We can have two intervals. We can have no solution. We can have negative infinity to infinity. We can have a lot of different possible answers. Don't try to generalize. Don't try to come up with rules that my answer is going to look like this in these situations. Just go through the steps. Every time, just go through the steps. Get the inequality so that it's x and x. Give them colors. Put those inequalities above the number line. And then just go back to blue and red, or blue or red, depending on what the original problem called for. Get your answer on the number line. Take that answer from the number line and put it in interval notation. That's what we're going to do every